So here we're asked to sketch the graph of the function f at x equals ln x squared minus 9. So the first thing we're going to do here is we're going to take our, find our first derivative and our second derivative. So our first derivative, we've got to use the chain rule here. Our outer function is the ln function, so it's going to be 1 over x squared minus 9 times the derivative of that inner function, which is just 2x. So we want to have this in simplified as much as possible and in factored form. So in factored form, this would be 2x over, and we can factor the denominator to x minus 3x plus 3. Now let's take our second derivative here. And for our second derivative, let's see, we want to use quotient rule here because we've got 2x over x squared minus 9. So we want the derivative of the numerator, which is just going to be 2, times the denominator, x squared minus 9, minus our numerator, 2x, times the derivative of the denominator, which is 2x. And this is all going to be over x squared minus 9, all squared. Now we want to simplify this and factor it here. So let's expand out our brackets here. We'll have 2x squared minus 18 minus 4x squared. We can go right ahead and factor the denominator. That's going to be x minus 3, x plus 3. Both of these guys are squared. Okay. And then let's simplify up in the numerator here. So we'll have negative 2x squared minus 18 all over x minus 3 squared x plus 3 squared, which is going to be equal to, if we factor out the negative 2, I guess, we'll have negative 2 x squared minus 9, sorry, x squared plus 9 all over x minus 3 x plus 3 squared squared. And there's our second derivative. So once we have our first and our second derivative, we can start looking at going through these steps to sketch the graph of our function. So first thing we want to consider is the domain. And let's remember what our original function is here. It's y equals ln x squared minus 9. So the restriction on our domain comes from the ln function. You cannot take the ln of a negative number or ln of 0. So that argument of the ln function, x squared minus 9, must be greater than 0. This means that x squared must be greater than 9, or that x must be greater than positive 3 or less than negative 3. So the simplest way of writing this is that our domain is going to be x is an element of real numbers, okay, such that the absolute value of x must be greater than 3, or the only valid x values we can have must be further away from 0 than 3, more than 3 units away from 0. What about our asymptotes? Well, let's see. Ln x, let's just write this off to the side here. If we consider the graph of ln x, it looks like this, okay? It's got an asymptote at x equals 0. So our curve approaches x equals 0, but never exactly reaches it. So our asymptote for our function here is going to be where not x equals 0, but where the argument of the ln function equals 0. So our vertical asymptote is going to be where x squared minus 9, that thing that is inside our ln function, is equal to 0. And this, of course, factors x minus 3, x plus 3 equals 0. So we have two vertical asymptotes at x equals positive 3 and x equals negative 3. We don't have any horizontal asymptotes, but we probably want to consider the end behavior here. And we can do that by evaluating the limit as x goes to positive infinity of our function, ln x squared minus 9, and the limit as x goes to negative infinity of our function. Well, let's think about what's going on here. As x gets very, very large, x squared will get very, very large. So x squared minus 9 is always going to be a positive value for large values of x, and that is going to be an ever increasingly large positive value, and taking the ln of it is just going to, it's still going to be positive and it's still going to be increasing. So this is going to tend towards positive infinity. Now as we go to negative infinity, negatives usually give us a problem with log functions because we can't take the log of a negative number. But because we are squaring it, as x goes to negative infinity, that x squared term right there is going to go to positive infinity. So subtracting 9 from it doesn't really matter. It's still going to a very, very large positive number, and the ln of a very, very large positive number is still a very large positive number. So our end behavior is going to go off to positive infinity at both ends of our graph. Our intercepts. Well, let's see. We can find our y-intercept. Our y-intercept occurs at x equals 0, but this is not in the domain of our function. Okay, we have to restrict ourselves to x values that are greater than 3 or x negative 3. So there's going to be no y-intercept. Now, what about our x-intercept? Well, for our x-intercepts, let's set y equal to 0. So our function here is x squared ln of x squared minus 9. How do we solve this equation here? Well, we can imagine raising both sides as exponents to the base e, or converting this logarithmic equation into a exponential equation. So if we imagine doing something like this, that e and that ln cancel out, and we're left with e to the 0, which is 1, equals x squared minus 9. Or, let's just bring the 9 over to the other side here. X squared equals 10. So x is going to equal plus or minus root 10, which is plus or minus about 3.16. So we have two x-intercepts, one positive and one negative. Let's find our intervals of increase / decrease and our possible maximum and minimum values. So we're looking for our critical numbers, where our derivative is 0, or where our derivative does not exist. So our derivative was 2x over x minus 3, x plus 3. It's going to equal 0. Well, that's going to equal 0 at 2x equals 0 or x equals 0, but x equals 0 is not in the domain. So that's not a critical number. Where does this derivative not exist? Well, it's not going to exist where the denominator is equal to 0. So it does not exist at x equals positive and negative 3. So those are going to be our only two critical numbers. And we know what those critical numbers represent. They are vertical asymptotes. So let's just sketch out our table of increasing and decreasing. We're going to have intervals from negative infinity to negative 3, from negative 3 to positive 3, and then from positive 3 to positive infinity. And we're checking each sign, the sign of each term in our first derivative to figure out what the sign of our first derivative is and what that tells us about our function. First thing is, this entire section of the graph of our table we can ignore because the function is not defined between x equals -3 and x equals +3. So from negative infinity to -3, this is going to be negative, negative, and negative. So our first derivative is going to be negative. From +3 to positive infinity, we're going to have positive, positive, and positive. Okay, so our function is going to be decreasing and then increasing, but we have no local max or min, because there are no points where it changes from increasing to decreasing. What about our concavity? Well, again, we're going to look at where our second derivative is equal to 0, where our second derivative does not exist. Our second derivative is -2x squared plus 9 all over x squared minus 9 squared. It is going to equal 0 where x squared plus 9 equals 0, but there's no solution there. It is not going to exist where, well, x squared minus 9 all squared equals 0, so where x squared minus 9 equals 0. So we've solved this already. We know that solutions are x equals positive and -3. So those are our sort of our critical points for the concavity. And again, we know what these lines are. These are vertical asymptotes. So if we set up our table here, we're going to have intervals from negative infinity to -3, -3 to +3, +3 to positive infinity, and we want to check the sign of each one of our terms in our second derivative. -2, x squared plus 9, x squared minus 9, all squared. We're using this to figure out the sign of our second derivative and what it tells us about the function. So again, we can ignore this middle interval because our function does not exist in that interval. -2 is going to be negative everywhere. X squared minus 9 all squared. Well, let's see, x squared plus 9 is going to be positive everywhere. Oh, this term is going to be positive everywhere because we're squaring everything. So our second derivative is always going to be negative. Our curve is always going to be concave down. So let's put all this information together here and try to sketch our graph. We're going to start with, let's start with our asymptotes, because we know that we've got an asymptote here at x equals -3, another one over here at x equals +3. We know that the function is not defined in between those two asymptotes. We had x-intercepts at 3.16, sorry, -3.16 and +3.16. So 3.16, -3.16. We had no local maximum and minima, and we had no points of inflection to plot. So we've plotted all the points that we can. The information we had about our intervals of increase and decrease were that it was decreasing here and increasing here. It was concave down here, concave down in this interval as well. All right. And oh, the one thing that I forgot was our end behavior. So our end behavior was as x goes to -infinity, the graph went off to -infinity, went to positive infinity, and as x went to positive infinity, the graph went on to positive infinity. So I want to draw a smooth curve through the points that I have drawn, which if I start from the left, my curve has to be decreasing and concave down. So it's just going to come along like this and then head down like that. Starting from the other asymptote and going to the right, it has to be increasing, so it's got to come up, go through that intercept, and match up with my end behavior. And in between, there's nothing because the function is undefined there. So there's the graph of ln of x squared minus 9.